Thank you very much, Dev. So today I'm going to talk to you about the research that I did for my PhD, which largely involved developing a method for free-falling dynamically scaled models using Foraminifera as an example. So I imagine your first question is, what is a Foraminifera? So generally, I'm going to call them forams because that's just easier. They're a single cell that lives in the ocean, and they produce a calcium carbonate shell on the outside of them, you can see here. And they're typically less than 1 millimeter in maximum length. And some species have spines, such as the one you can see here. And some species also have symbionts, which are these sort of gold brown that you can see here. And during the day, these photosynthetic symbionts are streamed out to the surface of the test, so they can access sunlight. And even those species that do have symbionts actually eat other plankton, taking on prey several times their own size. So here we have a foraminiferal shell or test, and they grow in a spiral pattern. So start off with a single chamber, and as the cell grows, they expand, increasing the number of chambers like so. We also have pores, which are small holes that you can see circled here, which the cytoplasm can move through, as well as these larger openings called apertures. Some species only have one aperture. Some species like this one have more. So here is another example of a foram with spines. And here's some surface scans and X-rays of forams, so you can get an idea of sort of the general morphology. Can be quite different between species. And when a foram dies or undergoes a reproduction event, the cytoplasm actually leaves that test or shell. So there's a hollow space inside that's filled with water. And it's actually these hollow tests that we're interested in looking at the sinking velocities of. And interestingly, each species has a uniquely shaped test. And there's over 600 morphospecies in the fossil record. So here's just a few examples of some living forams, again, to give you an idea of the sort of diversity of shape. From things that are relatively spherical, things that are unusual shapes. So why are we actually interested in forams and, in fact, their sinking speeds? So the focus of my PhD was to examine sinking speed of these tests and see how it relates to their shape. And there's a few different reasons why we might be interested in foraminiferal shape, sinking speed. First of all, because they're important in carbon storage. So as you're probably aware, carbon dioxide dissolves into the ocean. It's used by phytoplankton in respiration, and it's also used by forams whilst they're making their test. So the test is calcium carbonate, and the phytoplankton pick up the carbon dioxide and it's used in respiration. It's converted into organic compounds, and then plankton, including forams, consume the phytoplankton, and then the carbon is integrated into them. And when the foram dies, the test sinks to the ocean floor, and that removes the carbon that is stored in the calcium carbonate from the ocean. So it no longer part of the atmosphere. But whilst the test is sinking to the ocean floor, there is some dissolution going on. So that's the dissolving of the calcium carbonate. So there's some loss of calcium carbonate before it reaches the ocean floor. When it reaches the ocean floor, the test is buried by a constant rain of the forams, other organic matter, and this over geological time becomes rock. And the sinking speeds affect how quickly carbon is moved from the ocean surface layers to the deeper ocean. So this is an important variable in climate change models. So that's one reason we're interested in forams and their sinking speeds. Another important thing is actually dating rocks. So when paleontologists and geologists want to look at aging of rocks, they actually use forams to do this. So because forams are buried constantly, they can look to see what species are present in any given piece of rock, and they can use that, what species are present at any given point in time, to age that piece of rock. And that's important also in oil exploration. They can use also the color of the forams, which changes according to the depth and temperature which they've been stored, and these are a good predictor of where oil might be stored. So forams were sort of the importance of them was first really noticed during the Challenger expedition. This was a 4-year expedition from 1872 to 1876, really laid the foundation for modern oceanography. And it was during this expedition that the ocean floor was sampled at different points, and forams were found in 6 deposits. So this here is a jar of such a sample from the ocean floor, and the ocean floor is essentially covered in mud. It's so densely packed with forams that in places it's known as foraminifera ooze. And modern estimates suggest that forams cover around 40% of the ocean floor and account for 23 to 56% of calcium carbonate production. So again, these are huge producers of calcium carbonate, and understanding how rapidly carbon is removed from the ocean and stored in long-term storage is really important variable to include in climate change models. So another important thing is the paleo environment. So the very earliest studies that looked at reconstructing the Earth's temperature is forams. As the test is made from calcium and magnesium and the trace elements and isotopes that are present in the seawater when it's alive, the relative ratios of those elements is preserved in the test after it's buried on the ocean floor. So if we take a foram that's been buried in the ocean floor, say from 10,000 years ago, the elements and isotope ratios in the test can be determined, and from that you can get a picture of what the temperature of the ocean was at the time that the foram was alive. So this principle also applies for salinity, and we can also look simply to see what kind of species are present at any given time. So this graph here, we have mean sea surface temperature from 0 at the top here to 27 at the bottom, and along the x-axis here we have different species, and this is their relative abundance. Some species are only found in cold waters, some species are only found in tropical waters, and so paleontologists can take ocean floor sediment samples and see what species are present. From that, infer what the temperature of the water was that the foram was alive in. And so if forams take a long time sinking from the surface layers where they live to the ocean floor where they're buried and preserved, then this could affect the reconstruction of the paleo environment. We can also use them to infer sea levels using similar methods. Another important thing is actually evolution. So because there's this constant rain of forams to the ocean floor, each successive generation is actually preserved in the sediment. So you can look at an ocean core sample, you can go back and see how species change over time. In fact, it's one of the few things where you can actually look at evolution of morphology and you have a very clear record of how things have changed. And forams have undergone 4 major mass extinction events. So you can see here some examples of forams from the Cretaceous period. So the mass extinction at 65 million years ago, one that famously killed off the dinosaurs. Forams went through the same mass extinction event and their numbers drastically dropped. And then during the Paleogene, we see evolution of the similar forms of forams. And then you see the same thing again in the Neogene. So we see repeated evolution of similar forms. And this is convergent evolution. Exactly what pressures are being placed on forams, nobody really knows. they don't have active predators, so they are certainly eaten by filter feeders. They don't actively seek them out. So it's possible that sinking speeds is actually an important variable, and some work that was published just last month showed that foram desertification over the last 16 million years, partly driven by the cooling ocean. As the ocean surface layers cooled, it provided new habitat niches, which forams filled as food supplies and oxygen levels increased at lower depth, driven by that cooler sinking water. And this suggests that the evolution of morphologies could be driven by the need to maintain specific depth habitats within the ocean. So you can see here some artistic representations. These are the surface waters. And then as we move deeper, we find different shapes of forams. And so the suggestion is that actually their morphologies have been driven by this need to maintain a specific depth within the ocean to get the nutrients that they require. So now you know a little bit about why you might be interested in measuring sinking speeds. How do we actually go about measuring them? So forams are tiny. I mean, not on the same scale as bacteria or even some diatoms. They're small enough to make seeing them really tricky with the naked eye. So here is a foram. This is the tip of a paintbrush. You can see it's pretty small, quite difficult to manipulate. And I actually tried recording some in some trial experiments that I did, and you can see the small white dot moving down the water column here. And this is the one piece of footage that I got from trying this around 20 times. So they're small enough to make seeing them without magnification really quite tricky, but they sink fairly rapidly. Actually tracking them with some sort of moving camera system would be quite difficult as well. So instead, I thought, well, why don't we use an enlarged model of them? So using models of different sizes is something that's commonly used in engineering to model vehicle design, as you can see here. These are used to in industry to look at drag impact on fuel efficiency, because it saves the companies money. Like, you can model something smaller and cheaper rather than building a full-size car or airplane. And so dynamic scaling is governed by something called pi theory. This states that any physical problem that can be expressed as equations can be rewritten using a series of dimensionless groups or pi terms. So for two systems to be similar, they share the same dimensionless pi terms. So for a model and the real life example to be the same, we need to share the same pi terms, and those terms need to be equal. So for our dynamically scaled models, we need three things to be the same. They must be the same shape, so they must be geometrically similar, which kind of follows. They must experience the same relative change in fluid flows. If those two conditions are met, they will experience the same balance of forces acting upon them. And then similitude is achieved, correctly dynamically scaled. Now, I'm certainly not the first person to make models of organisms. Stephen Vogel was a great pioneer of using models. So this example here, he was looking at squids and how they refill the mantle, which is this part of them here, while they're swimming. And in order to do this, he built a larger model so that he could measure through these holes here the pressure coefficient. And so because he's interested in fluid flows, he needs to match Reynolds number, and he's interested in pressure coefficient, so he needs to match the pressure coefficient. And those are the two dimensionless pi terms that he needs to match. And in order to do this, he used, instead of water, put the model in a flowing stream of air in a wind tunnel, because he had access to a wind tunnel, he didn't have access to a flume. And in order to match Reynolds number, we then needed the air to flow at a faster speed than the water would be, than the squid would be swimming through water. A more recent example is Stedler et al., where they're looking at the sandfish skink. So this is a lizard, lives in the sand, as you can see here, and they burrow through the sand looking for insects to eat. And interesting thing is, though, that they avoid inhaling sand. Fiddler et al. Were interested in how they managed to do this. So they 3D printed airways of the skink, 7 and 8 times larger than real life. And in order to match Reynolds number in this enlarged airway, they used just the model inside a box that was filled with helium rather than using air, so that the relative viscosity is increased, and they increase the speed of the helium flowing through the model compared to the real life breathing rates of the skink. Another example is some of the work done by Waldrop et al. Looking at lobster and crab antennules. So that's crab here, lobster in this case. And these are the sniffing organs of these organisms, and they wanted to understand how they work at a hydrodynamic level. So they modeled the antennules at a scale factor of 70 and matched the Reynolds number by increasing the viscosity by using mineral oil instead of water, and they use relatively slow speed. And finally, some of the largest models that I came across in the literature was actually looking at flagella bundling. So you can see here bacteria, flagella bundling together. And in order to investigate this, how this works, Kim et al. Used models that were 61,000 times larger than real life. And again, they're matching Reynolds number. And in order to match this, instead of using water, place these models of flagella within silicon oil and look at how they actually bundle together and how they can be unbundled as well. So you probably noticed that all of these models required Reynolds number to be matched as they looked at movement of fluids or organisms through fluids. And as you will certainly know, our Reynolds number is calculated using the density of the fluid, characteristic length, u speed, and mu dynamic viscosity. My PhD was looking to develop a free-falling dynamically scaled models, and the first step to examine those forces and equations governing the system so that we can determine what pi terms are needed to match. We have a sinking foram, and we know that at terminal velocity, the sum of the forces acting on the foram is 0. And those forces are drag, which is determined by the density of the seawater, shape of the object, which is represented by psi here, which is captured by CB, as well as the projected area of the foram. And RE is included, which is affected by that characteristic length, the viscosity of seawater. Then we also have buoyancy, which requires that we know the volume of the particle, and we have weight, which requires the volume of the particle, in this case the foram, and the density of it, as well as gravity. So now we know that Reynolds number and drag coefficient are the dimensionless numbers that need to be matched. For a sphere, another simple geometric shapes, there are data that have been gathered, which can have been sinking spheres and plotting out data points. We can curves have been generated, and from those curves there are known equations. So this is the relationship for a sphere, and some forams, which is this one, fairly spherical. So we could easily just apply these known equations and plug in the numbers for a foram and get a Reynolds number and a drag coefficient for this foram, because it's relatively spherical. And this species is also relatively spherical. However, some species really aren't that spherical. So for these, there are no known equations that can easily describe the relationship between drag coefficient and Reynolds number. So that's exactly what I set out to determine. So from the fact that we know that the sum of the forces acting upon the model is 0, we can generate a theoretical drag coefficient and Reynolds number curve. And then we can also generate some data points such as these, and we can draw a line through those and create an experimental curve. And at the point where these two curves intersect is the point where similitude has been achieved for a dynamically scaled model, the point where Reynolds number and drag coefficient are equal. So, as you may have noticed, there's a small problem. My question is, how fast do Foraminifera sink? And things that I need to know are Reynolds number and drag coefficient. They both involve this unknown sinking speed. In order to determine how fast the models are sinking, I needed to know the Reynolds number and drag coefficient. They didn't know that because I didn't know how fast they were sinking. So developed a methodology using dynamically scaled models that I'm going to talk you through in a second. Before talking through that methodology, how do we make models for forams? So there's previously been a study published in 1997 by Furbish and Arnold that looked at the effect of the spines that I mentioned earlier on sinking speeds of forams. And these used some simple beeswax models of forams that they stuck spines into and looked at how that altered their sinking speed. However, I wanted my model foram to be exactly the same. This is a real foram here. And using CT scanning, we can generate a very accurate model that's exactly the same as the real foram. Then we can use 3D printing to exactly replicate that. So here is this foram. You can see rotating here. It's this foram on a slide, and here is an enlarged model of that. And this satisfies that need for geometric similarity because these are exactly the same shape. So we have a method for making a model foram, and we can look at how we need to calculate the equations that we need to calculate the sinking speed. We have again our sinking foram, and we have on this side the equation is going to be for the real foram in seawater. On this side we have model foram sinking in a mineral oil which is more viscous. So we know that the density of the fluid is going to be different, as is the viscosity, and we know that the shape of the foram and the model is going to be exactly the same because we're using 3D printing to generate that shape from a CT scan. And we know that the density of calcium carbonate in the case of the actual foram. We know the density of the plastic that we use to 3D print the model. And then we have the characteristic length, which is in the direction parallel to the sinking. And for the model, it scales as a scale factor times by that length. Area, again, we can measure the projected area, and this scales to the scale factor squared times the area. And so in order to find the sinking speed in seawater, we can simply substitute the values from the sinking experiment into the equations for the real life scale, including the change in density and viscosity, and then numerically find a solution, which I did use in MATLAB's F0 function. So this is the physically iterative approach that I developed in order to determine sinking speeds of real life forams. So I'm going to talk you through this. We start with some species that already have some published data. So we can use those to make an initial first guess about what kind of skies we might want to print our model at. Now, for those species that don't have any published data, we can use those equations that I mentioned earlier for a sphere and get an estimated drag coefficient and Reynolds number for a sinking sphere. Then we move on to actually 3D printing a model at that size. And the model needs to be fully cleaned and cured under UV light. And then we need to make sure that we have an accurate measure of the volume of that model, and then submerge that model into oil and remove any air bubbles from the inside. So here is a 3D printed model foram. Here's a needle from a syringe, and you can possibly make out a small air bubble here that I'm attempting to remove. And initial tests when I was running the first experiments for this showed that there was actually some resin and or bubbles inside the model. So some of them were sinking much faster than I would predict, and some of them were sinking much slower. So instead of using opaque plastic, such as the ones that are printed here, I 3D printed using a transparent plastic instead, so that I could see inside the model and make sure it was fully clear, and also that there was no air bubbles inside. Now, unfortunately, the refractive index of the resin that I was using to print the model from and the mineral oil that I was sinking it in was quite similar, so it was quite difficult to see them. But I did notice, as you might in this photograph, that when the model is under UV light, there's this faint blue glow. I illuminated the sinking tank with UV light to make it easier to see the transparent models. I mentioned in the tank, probably worth talking about it. So in order to limit the wall effects, that's the tendency of moving objects to be slowed down by nearby walls, I used a tank that was 1.8 meters in diameter and sufficiently tall to provide space for the model to accelerate to terminal velocity and then eliminate end effects as the model is reaching the bottom of the tank. So an advantage of using enlarged models is that I could actually film the majority of the tank using some standard webcams that were placed equidistant, as you can see in this diagram here on the tank wall. And because I have them at this 90-degree angle, I can actually track the model sinking in 3D. So I record the model sinking. Each model is released and recorded 5 times so that we can get an average of that sinking speed. And the video is processed and we track the model sinking through oil in order to acquire that sinking speed of the model. So here we have a sinking model. And then because the tank is cylindrical, I went and removed any distortion that might occur because of that rounded surface. And then we get, using some modified tracking code, we could find the vertical position of the model, and this is time, milliseconds. So we can track this model in its vertical and also in its horizontal position. Whilst the model was sinking, I also took high resolution images of the foram so that I could check what orientation it is sinking in, so that I can measure that characteristic length on the model on a computer digital model, and then also measure the projected area just by flipping that digital model around. And both of those can then be put into the calculations to calculate Reynolds number and drag coefficient. So I mentioned how the tank was chosen to limit Wall effects. However, some preliminary calculations that I did when I was looking at actually ordering the tank suggested that in order to remove the Wall effects completely, I would need a tank that was around 400 meters in diameter. So that seemed a little bit impractical. I settled for a 98% reduction in Wall effects, and then applied a correction factor to the drag coefficient to account for the presence of walls. So then once we've got our Reynolds number and drag coefficient curves, we can generate the point where the theoretical curve and the experimental curve intersect. I then need to look to see whether that prediction is interpolated or extrapolated. if it's extrapolated, i.e. it lies outside of the data points that I currently have, then I go ahead and predict the next scale that I need to 3D print the model at. If it's interpolated, if it lies between my data points, I can look to see if there's if the prediction sufficiently converges and there is a data point close by. So, and then I go ahead and 3D print the next model and generate more data points that I can put into the curve. And then again, check whether there's sufficient convergence. So I determined that if I had a data point within 5% of Reynolds number, then I could be satisfied that it sufficiently converged. So we can look at that in graph format. So here, we have Reynolds number on the x-axis, and we have drag coefficient on the y, and then each of these blue cyan points is an individual experiment, and the open blue circle is the average for those. And you can see here, so this is scale factor of 11, scale factor 15, and scale factor 17. And here is the point where this theoretical curve and the experimental curve cross over. So that's our predicted operating point. And there isn't a data point within 5%. I go ahead and 3D print another model at the predicted scale, and I check whether that changes the predictions. And in this case, sufficiently converged, and I was finished with that species. And then once that species is finished, I can use that scale size that I used for that specific species to inform the next species in the process. And then I go through the entire process again for every single species. So now I'll have a quick talk through some of the results that I had. So the number of iterations that I actually needed to go through, this is physical iterations, 3D printing a different model, was relatively few, especially towards the end of the experimental work where I had sort of refined the initial guessing process. And the two species needed more models. I think that's due to them having particularly difficult shapes that were quite tricky to remove all of the resin from and the bubbles. So as hard as I tried to make sure that they were as clean as possible and as bubble free as possible, I suspect that there was some bubble or resin still in there. So they took a few more iterations to reach convergence. So this just gives you an idea. This is the 33 species that I calculated sinking speeds for using this method. So each of these is a frontal view and then a side view. So you get an idea of the sort of variety of shape that I was looking at. The one out here by itself is one that's essentially spherical. So I didn't think you needed a side view of that. I also wanted to quantify the amount of error in the system. I 3D printed spheres at different sizes. I could compare them directly to the theoretical values from that equation that we saw earlier. And so this is the theoretical curve. And then here are my data points that I generated. And there is some separation between those two curves. It's fairly minimal and definitely in line with what other dynamically scaled studies have found and the sort of error within that system. So now we can have a look at some of the predicted sinking speeds in seawater. So given that the forams that I was looking at are relatively similar in size, there's actually quite a spread in sinking speeds from 1 centimeter per second to more than 6 centimeters per second. And we can look and see here we have, this is the volume of the wall. So remember me saying that forams are hollow. When I'm looking at them, it's an empty shell. It's filled with seawater. So along here we have just the volume of the wall itself, and then we have the sinking velocity here. And you can see that there's a reasonably nice relationship between the two. There are some separation points which I suspect that the variation there is due to shape. And I'm in the process of writing a paper that's exploring that. So hopefully you'll get to read that soon. Another exciting thing about this method is that it offers the ability to actually track the exact location of the model as it sinks. So previous studies looked at sinking speeds at 4 amps, simply dropped them in some water and measured with a stopwatch between 2 lines. But the method that I use, we have the exact XY positions of the 4 amp through time. And so you might have noticed when I showed this graph earlier, this is the vertical track, which is exactly what you might expect. Position goes downward through time. But when you look at the horizontal, it has this curved path. And this is actually because this particular species is not falling in a straight line as you might expect, actually following this helical path. So it's the species highlighted in red, and it follows this helical path as it sinks, as opposed to the relatively straight paths of the blue and the black data points there. And I'm actually currently examining how much of a difference this helical sinking path would make to the experienced velocity flowing past the surface of the model. So I mentioned earlier how dissolution is relatively important in terms of what elements and isotopes are preserved within the test. So if there's increased fluid flow over the surface of the 4 amp, then dissolution could be much higher than is currently assumed to be. And I'm looking at this with some collaborators at the University of Utrecht. So the other advantage of this methodology is that it's quite flexible. So see, the ocean's temperature varies with depth. So as you get deeper, temperature is colder. And studies that previously have looked at sinking speed have sank them within, a column of water that is kept at room temperature or at a specific temperature. But because the density and viscosity of water change with temperature, they can't examine the differences in sinking speed that this change in temperature might result in. However, because I can alter in the equations, I can alter the viscosity and density of seawater. I can actually model how fast a 4 amp would be sinking if the seawater is, say, 4 degrees when it's 3,500 meters below sea level. So this is important as well, because we know the surface of the sea is changing, climate change, the ocean temperatures are increasing. And so what impact does this increase in temperature have on the sinking velocity of things like 4 amps? And this could impact, the increase in surface temperatures could impact on where the boundary layers form within the ocean, how water is stratified. As I mentioned, if evolution of 4 amps is being driven by changes in sea temperature, and also changes in sea temperature could be leading to extinction of species. And additionally, it could impact on how much carbon is being stored in the deep ocean, and understanding those things is really important. So you might remember me mentioning the Challenger expedition and how they dredged the ocean floor, brought up large amounts of 4 amps from the sediments in the 1870s. So last year, the study compared some of these 4 amps. So you can see here a surface scan of the 4 amp, and here is sort of a cross section, and this is a single slice through the CT scan of a 4 amp from Challenger expedition. And at the top here, we have 4 amps taken from the modern ocean. And you can see that there is a reduction in the thickness of the wall, up to 50% reduction, most likely due to acidification of the oceans due to increased carbon emissions, which makes it more difficult for the 4 amp to secrete the calcium carbonate that makes up that test. And so I'm currently working to show how this reduction in testable thickness could result in reduction in sinking speeds. So here's some sort of preliminary results, and reduction in sinking velocity would then have the reduced have an impact on the amount of carbon that's reaching the deep ocean and being stored over geological time, so thereby reducing the damping effect that the oceans have in terms of limiting carbon dioxide levels in the atmosphere and therefore global warming. I feel it's also important that I should acknowledge some of the limitations of the method. Forams present considerable phenotypic variation. So here you can see these forams are all the same species, but they're different shapes. And I didn't capture that in my work, partly due to time constraints, partly due to a lack of CT scan data, which brings me to my next point. So foram being CT scanned, and CT scanning is relatively expensive. Although the costs are reducing and increasingly people are sharing their CT scans, so it's easier to access CT scans of species without you having to pay the cost of scanning them. Methodology can also be applied to other aquatic organisms. So here we have a selection of diatoms, range of different shapes, and the outside of the diatoms that you can see here is made from silica, which again is another important storage of carbon. So understanding how silica reaches the deep ocean is something that's an important field of study. It can also be applied to terrestrial systems, such as spores, seeds, and this is important in looking from an ecological point of view and understanding how species are distributed and how these spores and seeds travel through the environment. I should mention that whilst CT scans were necessary for my work because forams are hollow, if you have something like a seed that's relatively solid inside, and an external scan that captures that external morphology would be suitable. And so really that's the end of my talk, and I'd like to thank the Livy Hume Trust for funding my PhD, my collaborators, especially Stuart Humphreys, for his supervision and guidance, and really for his tremendous help with the MATLAB coding and introducing me to the intricacies of fluid dynamics. Patty helped with model production and the high resolution scan segmentation, and the rest of the physical ecology lab group offered support in many different ways. Before I invite questions, there's just one thing that I would like to ask you, which is I'm currently looking, I mentioned, at the shape of forams and how this impacts on their sinking speed. And so here we have a simple plot of drag coefficient and Reynolds number. I want to try and find a way that I can make comparisons at a given point of Reynolds number and their drag coefficient so that it's sort of equalized, because we know that drag coefficient is a function of Reynolds number. So if anybody has any thoughts about how we'd go about doing something like that, I would be really interested to hear them. Thank you very much for listening. The paper this presentation is based off is down here, and if you want to contact me via Twitter for any thoughts, I would be really grateful for that. Thank you very much for listening, and I'm happy to answer any of your questions.